University of Pavia, ETF in Zurich. His experience, my God, it lasted quite long. Technical staff of Bell, assistant professor of electrical engineering. And then he went to ARPANET, founder Center for the National Research Initiative, chairman and CEO, president, CNRI. So he's there already on the top. Membership is a fellow of AAAI and many committees and fellow of IEEE. You know, that itself tells you something, because that is the highest grade IEEE can honor or confirm on a individual engineer. So please give a big hand and welcome Dr. Kahn.
I'm going to talk to you today about the history and evolution of the Internet. I just wanted to give you a snapshot of what I'm going to try and cover. If you had raised this issue about Internet 5 years ago, most people probably had never heard of it. In fact, we were given an award from InfoWorld magazine for Product of the Year in 1993, which was the first time they ever gave a product to something that was Product of the Year that was 20 years old. The White House reported that in 1998, 1/3 of the growth, the economic growth in the United States was due to the Internet, things related to the Internet, which means that its reach is now extremely pervasive. It's got to be touching most aspects of society. And while we yet haven't figured out how to move physical entities through the Internet, the role of information processing and information itself has become fundamental in society in electronic form. So we're now in a very interesting formative stage where the Internet is about to transform itself yet into some future state that very few of us can probably predict accurately. I'm going to try and give you some view of sort of how we got started, how the Internet came into being and evolved, a little bit about some of the work that has been tried in terms of building very high-speed networks, and finally some comments about its relationship to what I call the national information infrastructure. And we're going to take a short break, if I can fit all that into roughly an hour, and then we'll come back and talk a little bit about a particular notion that I've been developing called the digital object infrastructure, which is sort of reinventing the Internet, but at a higher level in the conceptual space. And so we'll do that after the break, and then take any questions that you might have. Yeah, I'm aware of that, but I don't know what to do about that exactly. I can hold it, I suppose. Clip it to my nose.
You get a loose connection down somewhere where it's plugged in or something.
Yeah, like it makes static.
Okay, Todd, if you're going to have to hold that, you could use the wireless mic.
Is this not the wireless mic?
It's on your table.
Put that in your pocket.
That's where I had it. Okay, so let's take a first look at what the history was leading up to the Internet. The question I'm asked more often than any other was, could we imagine, when this all started, what the Internet would have become today? And the answer is, I think, clearly not. We were doing a research project. The goal was to see if we could connect two or multiple networks together and make computers on those different nets of different types work together. This had been after the ARPANET had demonstrated that we could get heterogeneous computers to interact, but the real challenge here, which was the open architecture challenge, was how to build a system of federated networks as well and make the whole thing work. In order to envision what subsequently happened, you would have had to imagine the creation of the personal computer and the workstation, along with the attendant development of local area nets. Because back in the early 70s, when I was getting started on this work, all we had were the large time-sharing systems. So you could imagine maybe 100 organizations that might eventually connect, nothing like we have today. You would have had to predict, I think, the breakup of the Bell system, because as long as AT&T was in a dominant position, commercially, they had no interest in seeing the internet as a thing where anybody could plug in without having, you know, arrangements, contractual arrangements, proceed and succeed. I think without NSF getting involved, the Department of Defense would have kept too tight a rein on this, and so NSF's role was to open up the technology base developed by DARPA and let multiple options come to exist. You would have had to envision the success of NSF in creating the NSFnet, which really made it possible for the entire scientific community to communicate with each other. I think a lot of the credit really has to go to Congressman Boucher of Virginia, who introduced the Boucher Bill in 1993, which had the effect of enabling the National Science Foundation to open up a government facility to commercial use. You'd certainly have had to imagine the 90s regulatory environment, which basically stimulated a lot of this. And just to put things in proper perspective, I think, you know, while the exact words that the Vice President used were probably not accurate, he actually played a significant role in stimulating a lot of the development that happened roughly from the mid-1980s on. So all of those things would have had to have been understood clearly in order to see where we are now. Now, I think in the early 1990s, nobody realized that when people were talking about the information superhighway, which was his term for it, or the national information infrastructure, which was my term, that the internet would be it, because you would have had to imagine all of this stuff really coming into place. But having said that, there really is a challenge ahead of us. One is that to create something that will be like a national infrastructure for information really is something that's going to take a long-term commitment. It's not going to happen by natural market forces. It does need the help of a lot of focused R&D, a lot of test beds, and commercial involvement, different sorts. It needs to involve most, if not all, of the leading research and development groups, not only as creators of the technology, but also as early adopters, because a lot of this technology requires expertise in order to make use of. We need an accepted process that we understand in this country that can get us down a path of what I call coherence, convergence, and interoperability, because without that, we really don't have an infrastructure in the country. We just have a lot of independent pieces that may or may not play together. The test of all of this is whether we have actually lowered critical barriers to progress, and whether we've actually produced a more productive society and hopefully a more desirable one as well. So those are just some initial observations. If you look at the modern networking era, I'm going to date that to really the late 1960s, of which the pilot project, really the flagship project, was the ARPANET. This was an effort on the part of the Defense Advanced Research Projects Agency, then just known as ARPA, to figure out how to link computers of different kinds for the purpose of sharing resources. Their motivations are often confused. I mean, a lot of people who understood that some of the ideas in packet switching came out of early writings of Paul Barron at the RAND Corporation in the era of nuclear warfare think that the motivation was totally the military one, whereas in fact I think the more fundamental driving force was the scientific one, and to link the community together, where the military did understand that it had some potential defense objectives and defense capabilities, but that was not what was driving it. The ARPANET really was in the period from roughly 69 through 88. It was actually decommissioned in 1990, but it was sort of on a tail off after about 88. And roughly in 88 was when the NSFnet was brought up by the National Science Foundation. The ARPANET being a 50 kilobit net, the move to the NSFnet was a real ratchet up in speed, because their backbone started out at 1.5 megabits, which was a factor of 30 higher in bandwidth, and eventually became 45 megabits, and now they're pursuing activities that are at even higher speed. The notion of a commercial internet I date to roughly the 1990 timeframe. There was some early efforts in the late 80s, but the combination of UUNet and PSINet around 1990 was what started the commercial internet as we now know it. Of course, they could not interoperate with the NSFnet in those early days due to an acceptable use policy, But after the voucher bill, it all opened up, and then everybody was able to provide connectivity to everybody else. Starting in 1990, we had the very first of the very high-speed networking experiments, the so-called gigabit testbeds. This was an effort that I actually proposed and led during its period of operation. Those testbeds, some of them are still in existence. Some of them were dismantled a few years ago. In fact, there was a period where, after we successfully demonstrated 2.4 gigabit connectivity in 5 different testbeds, many of the folks who were in a position to keep it going declared that, well, now that we know it's possible to do, let's dismantle them because we don't need them, only to find out a year or two later that it was now a priority to have gigabits, and proceeded to try and ratchet up the whole system again. Only this next phase is going to be commercial rather than government-sponsored. From 1995 on, there was commercial OC3 access at 155 megabits per second, probably most notably due to the efforts of MCI on their VBNS, which was funded by MCI. And from 1998 to the present, the whole government NGI program has been in place. And I think right now the focus on almost everybody's part is to understand what to do with this kind of capability, not how to build it or even deploy it. So that's just sort of an oversight, a view of the whole thing from on top. Some of the key milestones, well, of course, I guess I left off this list perhaps the most important one, which was the paper that I wrote with a colleague of mine back in 1973, which described a set of protocols for interconnecting packet communication nets. But those protocols were implemented in the 1974-5 time frame, and I believe in 1976 the first 2 network tests were conducted, and in 1977 the first 3 network tests. So we actually have clear documentation of the 3 network tests, which involved the packet radio system, which was really the first incarnation of what's now known as CDMA technology, packet satellite system, which is sort of like an Ethernet in the sky, except with longer delays, and the ARPANET itself. In 1980, the TCP/IP protocols were defined as a standard by the Department of Defense. In 1983, the actual conversion of the ARPANET to those protocols occurred. I actually managed that transition. Occurred on January the 1st, 83, but in fact, that transition occurred over close to a 6-month period, as not everybody was ready to convert on the first. In 1988, the NSFnet became operational. It was a contract from NSF to Merit, a nonprofit organization in Michigan, with support from MCI and IBM. The ARPANET decommissioned then in 1990, and in about roughly 92, the NSF got ratcheted up to 45 megabits per second. And by 1995, there was so much commercial activity that NSF decided they no longer had to provide support for the NSF itself. So those are some of the key internet milestones, at least that's all I could fit on the slide. In terms of thrusts, this is again one of those interesting issues. No activity with as broad an impact as the internet could possibly have happened without the support of many, many people, not only in different areas, but around the world. And therefore, anybody who has ever touched the field of computer networking at any point in time really does feel a sense of paternity for what's actually happened, because every one of those people has made contributions. And I think that the world would be a better place if we could just simply stick to a litany of who did what, rather than try and put labels on the whole thing, because at this point, we have too many fathers of the internet out there for anybody to really sort out what paternity really means. In terms of a community, if you go back to the days of the ARPANET, that's really where the networking community first started. And nothing changed when we got to the internet. I mean, people were still doing the same kind of things after. But in terms of technology, it made a very big difference, because the ARPANET was a single network run by a single organization, and the internet itself became a mechanism by which multiple networks could federate together without there being a central body in charge of the whole thing. So it opened it up to the kind of proliferation that we've now seen around the world. In the United States alone, there are something on the order of 5,000 internet service providers today, probably closer to 8,000 or 10,000 around the world. And I suspect that will all sort out in time. There are only a few of them that are really broad national providers. A lot of them are ma and pa type operations in local areas. But if you go back to the early days of this century, I don't know how many car companies there were, but there had to be hundreds. And now there are, just a handful of really big car companies when it all sorted out. I think the same thing will happen here in time. But right now, it's fair game for everybody. Not only is it fair game for everybody at the provision of internet service, but I meet more parents who are proud to introduce their 11 and 13-year-old kids who are running businesses out of their bedrooms, doing web pages and making money at it. And so it's really introducing entrepreneurism at a very early age at the grassroots level. So you have a community that really goes back to the earliest days of the ARPANET. You have technology. I would define the internet technology as really starting with the TCP/IP protocols because it's what really defines what the internet is today. At the level of management, you have a whole other collection of individuals who've been involved in overseeing this thing from an administrative point of view. I played partly that role for a while, although I'm probably more involved in the technology side of it by far. But the whole idea of managing IP addresses and domain names and acceptable use policies and the like has really been the domain of government for a long time. It's now changing. And then you have the whole commercialization thrust, and much of that happened with private investment. It's amazing that there are actually some people who have, very prominent people who've actually given talks saying that the internet was a perfect example of why you don't need government research because commercial industry could do it all themselves. Completely forgetting about the fact that there wouldn't have been any opportunity if the government hadn't nurtured this for some 25 years before. So, okay. Some of the building blocks, you clearly have packet switching as a technology, the ARPANET as the realization of it. Time sharing and operating systems are critical to this. The whole notion of open architecture, by which I mean defined interfaces, defined protocols, common objects that can pass back and forth between the networks and the hosts. The notion of protocol layering, which was actually an interesting concept out of the ARPANET days that would allow you to build on top of other pieces of software in this open architecture fashion at the host level. The existing computer and telecommunications infrastructure were used right from day one. Nobody reinvented the idea of a digital communication line as part of this. They just made use of it in new and innovative ways. And there were a lot of interesting other networks. Of course, the microelectronics field has just fueled this whole activity right from day one. In terms of the community, I'm going to go through those first few activities for you here. We started out with the ARPANET community because that was the only network that was around. And things that people did are not that different from what people do today. Send email, file transfers, do remote logins, essentially run programs at many different locations, share information. That was all happening from the early 1970s. The evolution of the network, ways to evolve it, sharing of information, that all happened back then. On the technology side, the real question was how do you interconnect multiple networks? And we were focusing on 3 packet networks, but in fact, if you had other networks, you could have incorporated them as well. To me, the intellectual contribution to this whole thing was the whole idea of open architecture networking. The TCP/IP protocols were merely the realization of that concept in a tangible way, and this whole field was really enabled by DARPA being willing to support it over a long period of time. Now, I was at DARPA at the time, so it was actually something that I was really privileged to be able to push at that time. So I was not only doing the technical work, I was also funding the community to work on this during that whole period. So the idea was that we would overlay this internet architecture on top of the ARPANET. The ARPANET was out there, it had all the computers. These other networks couldn't possibly have computers on them because the computers were all these big mainframes at the time, or time-sharing systems. So if you took a packet radio net where the radios were mobile, actually I would call them luggable rather than portable, you wouldn't expect to have a multi-million-dollar time-sharing system along with it. So you really needed to get to some of these other networks in order to make the connectivity part of it work. Well, the question then was, if you took 2 different networks and tried to interface them, how would you make that work? And so the idea that I introduced was that of a black box that would go between it. We called them gateways back at that time. Nowadays you'd call it a router, but it basically was the impedance matcher between the two nets. That is, the nets might have different packet sizes. It would adjust the sizes of the packets. They'd have different error messages. They'd have different interfaces. All of the details about the nets were different, so you couldn't just take the two interfaces and plug them together, even if the interfaces were plug compatible, which they weren't. And so that turned out in due course to be a very big business for certain companies like Cisco, which essentially kind of own that business today. There was a notion of an end-to-end protocol that we introduced so that at the two ends the host could make sure that things were showing up right. And the IP protocol was simply what was used to do best efforts packet delivery, and it was implemented mainly in the gateways. So the gateways could tell when a packet came in how to reroute it. Now, we could go back and spend some time talking about the deficiencies of the ARPANET and why you couldn't do this with that and why the protocols for the ARPANET didn't support it. But because we don't have enough time, I'm not going to go down that path. Just suffice it to say that you really needed to rethink the whole architectural notion to networking in order to make an internet happen. And that's, in fact, exactly what we did in the early 70s. On the management side, there are a lot of people who have been involved. I actually handled all of the initial management of it from roughly 72 through 76. And then again, I picked it up briefly in the early 80s. I hired a fellow who was then at Stanford, who had actually collaborated on some work with the ARPANET before then, named Vint Cerf, who's now a senior VP at MCI. And Vint and I have collaborated for a long time. He worked for me at DARPA during that period. He actually ran the internet program from 76 through 82. Barry Liner, another gentleman who worked for me, ran it from 83 through 85. In 85, it transitioned over to NSF. I might point out that both Cerf and Liner and I had just left DARPA by that point in time, so in fact it was a natural point of transition in any event. Steve Wolf was the driving force for pushing the NSF forward in the networking field. He ran their networking program at least from the 1987 to 1995 timeframe when he left to go to Cisco. But in fact, he had been a strong proponent for networking even before the 87 timeframe. The NSFnet is largely due to his efforts. His successors were Jane Cavanis and George Strawn. Now, in terms of management structures, it's interesting. Before 1978, there really weren't any. I mean, today you probably read about domain addresses in the Washington Post and all the struggle for, you know, how much money is needed to do this, and should you charge $1 or $50 per domain name. But in those days, I used to keep all of the domain names on a little index card in my pocket. Somebody wanted to get on the internet, they'd call me up, write it down. And when the card got filled up, I decided it was too much effort to have to manage 2 index cards. And so I asked John Postel at ISI to handle that job, and he became legend in that field for doing what everybody viewed as an administrative green eye shade job for a long time, but he did it to the point where it really became a linchpin of operation of the whole internet. In 1978, we established something called the Internet Configuration Control Board, the ICCB, if you see it over here. And the reason that I did that was I was very concerned that if something happened to either myself or to Vint Cerf, who was then running the program for me, that nobody would know enough to be able to continue running it. And so we brought together roughly 10 or 12 of the key implementers from the community to form the ICCB. And their job was to help other people figure out how to get onto this nascent internet, which was at that point an overlay on the ARPANET. Different protocols, they weren't the standards yet. And the ICCB functioned very well until roughly 1983, when Barry Liner took over the program. These group of 12 people, in order to discuss protocols, were in such demand that people would just call us and beg to sit in on the meeting. So you couldn't hold a meeting of those 12 people without inviting another 50, and later 100. By 1983, it was like 200 or 300 people that you had to invite just to hold a meeting of 12. So it was like a theater in the round, and people just wanted to be there to listen to the discussion. What Barry, jointly with Dave Clark from MIT, did at that point was to reorganize the structure and create something called the Internet Activities Board, or IAB. And under the IAB, they formed a set of 10 task forces working on different problem areas like end-to-end protocols, autonomous systems, security, and so forth. And one of them was called Internet Engineering Task Force. That was one of the 10 task forces. And by 1986 or so, the number of task forces had grown from the initial 10 to over 50. And the Internet Engineering Task Force, which had the charter of worrying about near-term developments in the Internet, was asked to take over the management of all the task forces. And that's how the IETF has come to be essentially the standards-making body of the Internet today. In 1986, the federal government decided to get organized, and they set up a Federal Research Internet Coordinating Council, or the FRIC. That was a rather informal group which later got formalized under the President's Science Advisor as the Federal Networking Council. And that is the group that today oversees federal policy for networking. In the early 1990s, as the Internet was starting to become more and more commercialized, my organization, which had the basic responsibility for running all the IETF activities under a cooperative agreement with the National Science Foundation, came to the conclusion that we needed a different structure in order to oversee all this protocol development, because there was too much commercial interest, and therefore it really needed more than just partial attention to this. And so we ended up forming something called the Internet Society. Myself and 3 other people signed the incorporation papers in 1992, and thus the Internet Society was formed as a professional society for users and firms that were dealing with the Internet. And it still plays a key role in a number of areas. It runs probably the preeminent international conference on communication networks called INET, and it also is formally the home of the standards process, and as they adopt the rules by which that works. The IETF, which is the one that does the work, is actually under our control. In 1998, the ICANN was formed, the Internet Corporation for Assigned Names and Numbers, and that's now gradually becoming the public sector authority on what historically has been a role that the government has maintained. It's one of the last vestiges of direct government involvement. There are many other structures, but this is a group of them. In the area of management, there were a variety of areas that were addressed. These are just some of them. I won't go into them in more detail, but it's been an area that has received a lot of federal attention. On the commercial side, well, I mentioned UUNet and PSINet were the first 2. UUNet was actually an outgrowth of a seismic data effort. The UU stands for Unix to Unix communication, and it was originally set up as a nonprofit. PSINet was actually, I don't know what the right term is, a molting out of something called NYSERNet, which was a New York State educational and research network that would set up with support from NSF, the state of New York, and NINEX. PSINet started out as a for-profit organization and really pushed UUNet into becoming a for-profit corporation, even though I think it wasn't their interest or intent to do that. I don't think the people who started it minded that much, because a few years ago, Metropolitan Fiber approached the then chairman of the board, Rick Adams, to buy UUNet and offered him $8 million to buy it. And my understanding is that the reason he didn't sell was because he thought it was worth $12 million. 1 year later, Metropolitan Fiber came back and paid $2 billion for the same company. So I don't think he minded having gone commercial on at that level. On the internet software side of the world, well, clearly email, which has been around for a long time, is clearly one of the main applications. In fact, I think it's still the killer application on the internet. But the web has continued to grow over time as more and more content is now being put up on the net. And the thing that really made that possible was the introduction of the internet browser, based on the work of some people at Illinois, Mosaic, which later led to Netscape Communications. This was all really facilitated by the work that Tim Berners-Lee had done on the creation of the web protocols, which was not going very far before that time because it was too hard for people to actually make use of it. But with the introduction of a point-and-click interface to the web protocols, it really made it possible for most people to really grasp that and make easy use of it. On the commercial side, a lot of websites. There was the MCI mail connection. The interesting thing is that most people understand that the whole internet was a research kind of experiment for a long time, and that today it's mostly commercial, but very few people can actually tell you what the first commercial application was on the internet. And it turned out that it was one that my organization actually did in 1989, which was the connection of MCI mail to the internet. I don't know that MCI really understood what the power was of that connection at the time. But as they began to use MCI mail, they suddenly discovered that they had the ability in their system to communicate with the whole internet. And I am sure to this day that they thought it was just a natural part of the MCI mail system rather than something that was built in. In any event, it turned out to be very powerful and was what enabled them to be so successful in developing the NSFNet, I might add. And then there was the whole federal enablement due to the voucher bill and all the subsequent agency policies that followed up on that. So what do we have today in terms of an NII? We clearly have the internet, and we could just simply say the internet plus email and the web, which is what most people use it for, is really what the NII is. These all exist. They can support a lot of future applications, but unfortunately this is a very limited notion, and I'm going to say a little bit more about that in a bit. But I think the easiest way to get into the subject is to talk about how hard it is to create advanced infrastructure in this country. I mean, getting the internet in place was a result of federal investment. They could buy the circuits, invest in the switches, put the facilities out there. But as a practical matter, the government can't really do this over and over and over and over again. It ought not to be their job. Except that where really advanced research is required to make these things happen, they can invest in advanced research, and they do. The question then is, when you have the technology that can enable advanced infrastructure to be deployed in the country, whose job is it to deploy it? I think even the federal government, most ardent supporters of advanced infrastructure would say the private sector ought to do it. But in order for the private sector to do it, they either need a market that would justify its deployment, or they need the dollars to pay for it through some kind of a government contract or whatever, maybe a privately led contract. And yet when you're talking about, billions of bits a second or higher speed nets, you're talking about enormous sums of money, hundreds of millions of dollars, maybe even up to as much as $1 billion, depending on what we're talking about. The equipment suppliers have very much the same kind of concerns. They're not going to build the equipment to commercial spec until there's somebody who's going to buy it from them. Likewise, application developers aren't going to build applications that need advanced infrastructure to work if it's not deployed. And so you end up with this chicken and egg conundrum whereby if the infrastructure were out there, the technology and applications would be widespread. And yet they really can't happen until the other one happens. And so this is the classic conundrum. So what you have here is a situation where this is sort of the natural course of events. Companies can build computer hardware and software that runs faster and faster, simply because it doesn't have to be a nationwide thing and all federated. So you find computers that go at faster and faster speeds. The interfaces on them tend to go at whatever the fastest speed is that they can connect to in an affordable way. As a result of those computers, you tend to get local area nets that will work as fast as the interfaces and buses on those systems will work, and they can be deployed in a local environment. This doesn't require a national level investment of hundreds of millions of dollars. And likewise, once you have these two in place, the research community will develop initial applications on that base. But now the question is, how do you federate this all into a national level base where they can interface with their colleagues from Berkeley or MIT or Illinois or Texas or wherever? And that gets you into the question of building the WANs and the MANs, the wide area nets, the metropolitan area nets, and that's really where the stumbling block comes from. So I'm going to give you some lessons that I've learned over time. Here's a statement of the problem. If you've got the computing equipment at the speed that you need, if you could get network equipment at the speed you need, given that you have candidate applications, adequate support, and even industry incentives, how do you justify making the wide area network investments up front? And this issue really is a recurring one simply because of the fact that if we can figure out how to make the argument for building a 50 kilobit net, which was really hard back in the early 60s, because nobody understood that 50 kilobits was something you really needed for networking. They thought maybe 300 baud would be sufficient. How do you get to 1.5 megabits? Well, it's probably a leap of faith. You can make some arguments that the world really will be different, but it really is a leap of faith and only happens easily when it's affordable to make that step in terms of the cost of the lines. Well, how do you then get to a gigabit? If you're at a gigabit, how do you get to a terabit or a petabit or an exabit or a yotabit or a lotabit or whatever comes after that? So I think we need a strategy for dealing with this on a regular basis, and one that can allow us to use the current network to leverage the future. Let me just say, from my own experience, there are a few application drivers we currently know that will cause wide area networks to be, that can motivate it. Whether these are all economic is a different issue, but clearly the most fundamental one is multiplexing. I mean, fiber optic networks really began to be deployed in the United States in the late 1980s by AT&T. And the reason they did that was because they needed, it was an economic way of getting more voice channels. Okay, and so the need for more and more capacity at lower speed has in fact been driving a lot of the carriers to deploy fiber optics because they can do multiplexing. Yeah, was there a question over there?
Well, it was deployed by U.S. West, among others, and it was clear they really didn't need all those voice channels. Everybody on one side of town would have to be talking to everybody on the other side of town at the same time, and they weren't going to. So they were looking for their applications.
Many groups did that, but my recollection is that the first really transnational connections were done by AT&T around 1986 or 7 at something like 1.7 gigabits per second. If U.S. West did experiments back in those time frames, it would have had to be more localized to their region of the country. I don't think they would have done them nationally.
It wasn't justified by voice. It was, in their hearts, they knew it wasn't voice.
I'm sure there were a lot of other experiments that people were doing. I'm just saying that as an economic driver, as an economic motivator for people to put fiber optics, multiplexing has been traditionally one strong motivator. That's the only point I'm making with that point. The second motivator is where you want to essentially do real-time analysis, synthesis, and display of data. And where getting it from one place to another rapidly is really what's important. So for example, you know, if you had a radiological image at one location and a doctor wanted to look at it, and you know, if it took more than a tenth of a second to come up or a second to come up, he might not want to use that mode of operation, then it suddenly becomes irrelevant. On the other hand, if it took an hour to come across a very slow speed line, you could still get it there, but it would be too late to be, you know, practically useful. So that's another driver where you have a lot of data that you need to get somewhere for real-time purposes. We've got a lot of experience with parallel processing with multiple supercomputers. In fact, I funded some work on one of our test beds called CASA that linked Caltech, JPL, the San Diego Supercomputer Center, and Los Alamos. One of their experiments was to simulate the operation of a hydrogen fluoride laser, which I think at the time was one of the most powerful of the chemical lasers. And what they actually could do was simulate what was happening with hydrogen on one machine and fluorine on the other, and passing back a lot of the boundary condition information back and forth on those machines. And you could actually make the argument you know, that you could use an arbitrarily large amount of computing capacity and communication capacity to make that work as you ratcheted things up. Another possibility is sequential processing of large data sets, and we did an experiment on that down in the North Carolina region. Had to do with radiation oncology, where you take MRI data, ship it to a Cray computer in order to process it, to ship it to a silicon graphics machine to render it in some appropriate way, and then to put it to another machine that could actually display it in the hospital rooms so that the parties who were actually being operated on could be, the doctors could actually see how to position the beams in the hospital room in real time. So that was another example. I think the whole issue of remote interactive visualization is important. I sort of mentioned telemedicine as one example. It could be more than just radiology. It could be for real-time physical data. Another area that's kind of interesting to me is related to the use of the networks to handle logistics for processing job shopping of MEMS devices. The MEMS exchange is an activity that we currently run on the net. If you looked up the www.mems-exchange.org site, you'll see that you can design a whole process for fabricating MEMS devices, that you can ship designs into this unique process that you just designed, and that when the wafers are actually fabricated, they're moved from foundry to foundry to foundry in hermetically sealed wafers, and you can actually look at the results of that fabrication on remote microscopes attached to the internet from your own local site. You can actually download the software from the net in order to do that. Now, you actually have fairly fine resolution on these, and if you actually try to look at very big chunks of it with all the mechanical motions and the simulations involved, you can come up with justifications for high-speed data there as well. There are really 5 models I want to talk about very briefly. I'm not going to elaborate on these a whole lot, but model number 1 was what I call the gigabit testbed model, where the government essentially funds it as an R&D project. And we did that. It made the front page of the New York Times when we did. They estimated that industry put in close to $500 million into a project that the government put $20 million in. And we actually had 5 test beds up and running across the country. The problem with this approach is it's very hard. I mean, you've got to spend a lot of time and energy. The politics are fierce. There's a lot of political capital that you have to expend. It's not an obvious algorithm that you apply to make this work. It's all done in a voluntary fashion, hard to keep the efforts together. You get big gains, there's a lot of early experience, but it's hard to sustain this over the long term. Second model is what I call the government lead model, and this is where the government not only funds research, but they actually fund the deployment of an experimental wide area net and make it available. So the research sites might actually pay for local access and maybe even local equipment, whatever, although they may get that through government contracts too. Research is done as usual, but the government takes the lead. The NSF net was a good example of that. The problem with this is usually it's a contract to one supplier. Generally not a competitive environment, which results you often get limited geographic coverage. The research sites have trouble coming up with money. Not all of them can pay for local access. And in fact, if the government stops supporting the local guys, then the long haul stuff becomes difficult to sustain as well. The third one is what I call the carrier's lead model. And in fact, we had several of the carriers agree to make available secondary channels on their long-haul nets such that they could be made available to the research community. It turns out that the cost of this is pretty affordable. On the other hand, you're dealing with preemptible systems, and therefore nobody can really depend upon it being there, but it's a very low-cost way to actually build facilities. Unfortunately, after the government ended up deciding to pay for this capability, the carriers suddenly realized that making available secondary channels was not necessarily as lucrative for them, as profitable as actually selling primary channels, and so this is no longer an option as far as I'm concerned. On the other hand, in order to make this model work, you do need still a very big government commitment. We made some notion that you need about 100 sites to justify this, and if you assume that the local access costs might be as much as $500,000 a year, that sort of says you need a research program of at least 2 or 3 times that at each site, and it came to the hundreds of millions of dollars per year to keep this going, and we didn't think that was sustainable either. Another model is what I call the last mile company, which essentially takes the connectivity problem and puts it in the hands of a regulated organization. This is not one that ever appealed to any of the RBOCs or the cable companies as far as I could see. Most of them felt that owning the last mile access was a valuable asset to themselves in the long term. On the other hand, for most things that come into the house, there has been some attempt to try and get that all orchestrated. You don't have multiple streets in front of your house, you don't have multiple gas lines coming in, you don't have multiple power lines coming in, and even with this competitive power environment that we're running into, it'll still be a single cable that goes into your house for power purposes. And then the last model is what I call the visionary entrepreneur model, where if you just sort of do the economics of what people are likely to be willing to pay at the high end for this kind of throughput, there's enough money there to make something happen. The question is, who's willing to go for that limited market to make it happen? And this is something that we're still exploring at the present time. One group that's, you probably have all heard of Abilene, which is sort of a model 3 kind of scenario, or the VBNS, which is a Model 2. The High-Speed Connectivity Consortium is sort of a Model 5 effort, and this is something that DARPA is using to interconnected SuperNet project. The long-distance services come on the QuestNet, but they can be used for any commercial purposes. And the local services are basically made available through a number of different forums, including some of the telcos that are involved in some experimental projects, some of the power companies like DQE in Pittsburgh, which are in fact making available fiber, but they're also taking wavelengths on the same fiber for their commercial purposes while making some other wavelengths available for research purposes. The problem with the Model 5 view is that it really requires a rather philanthropic set of people to make that happen as well, because even if it's successful, it's going to be probably co-opted by somebody else very, very soon. So I think of all these approaches, the Model 5 one has the best chance of success, but it's also probably the most difficult one to pull off over a sustained period. So a few more comments about the National Information Infrastructure, and then I think we'll take a short break. This is a question people often ask. You know, well, given that we're doing the NII, will it be adequate? My problem is that I don't think we have a plan for a national information infrastructure. What we have at this point is some consensus that the internet is maybe the lower level piece of it, but what has to go above it is still anybody's guess. And instead of orchestrating what we have out there by way of, you know, some kind of, you know, global approach, what we have is the equivalent of commissioning a symphony by requesting a piccolo piece and a violin piece and a tuba piece and some drum pieces, and sort of taking what you get in, putting them together and calling it a symphony. It's not necessarily going to be symphonic. It may be more cacophonous than it is symphonic. That appears to be the path that we're going down for the most part. What could it be? Well, interoperability among all the components for suitable definitions, plug-and-play interfaces, easy assembly of components into systems. I'm not talking about just the physical ones. I'm talking about major software modules in different places. Interoperability between bundled systems. I mean, I think in time, as we get into high-speed nets, you're no longer going to go buy CD-ROMs from your local stores. What you're going to do is download software, and you're going to get bundled systems that are bundled by the equivalent of the people who now give you package systems. And you want to make sure that this bundle that comes from this group, Macrosoft, works with that bundled system which comes from Moon Systems, and that they all play together. But what's going to make that happen? Service performance specifications that can be met within broad envelopes, so you as a designer can design things and know you have a fighting shot at making it work. Scalable systems. But where are we now? We have some of these ingredients. The internet is certainly there. It's got some limitations, but we don't know what the NII is. We don't have a means of getting there. We don't know how it should work, or even how to go about resolving a lot of the most fundamental questions. So since I claim it doesn't exist yet, it's obviously not adequate for future applications. And until we come to grips with the fundamental issue of the process by which we're going to get convergence, we probably will never have one. I think this is the last slide. Let's see, yeah. This is the last of the slides. I just want to say what properties infrastructure really ought to have. if you really have something that's infrastructural, by definition, it lowers the barriers to something. Lowers the time to develop a new system, the time to create information, the time to locate it, the time to communicate it, lowers the cost, lowers size, weight, or power, increased reliability, or access to limited resources. Those are examples. If it doesn't do that, then my argument is it's not infrastructural. Now, infrastructure usually has some other properties that go along with it. It's normally ubiquitous. It's normally shareable. It normally is easy to understand. It's normally affordable, things like that. If it doesn't have those properties, if only the multimillionaires can afford it, it really isn't infrastructural. If it's too hard to understand, it's not infrastructural, and so forth. But if it doesn't have the property that having it around makes things easier to do, it really hasn't served its purpose. And I think at this stage of the game, we have not yet made it really a lot easier to build most of the things that we can imagine wanting to build. Now, some things have been enabled, like the World Wide Web, which is a fairly recent development, I think was greatly enabled by the existence of the internet. Because without the internet, it would have been almost impossible to imagine fielding something like the World Wide Web. So that's an example, but that's a very highly technical kind of creation. We can imagine lots of other things at a higher level that people could put together, like health systems, for example, where you might want to bring together an insurance company and a health provider, and you might want to bring some educational folks and maybe some payment organizations, so the whole thing can work together in a symbiotic way, and not have one person have to be an expert in everything, so that you can interface with all the things that are out there. So I'm going to come back after our break and talk about one example of a thing that we can in fact create as this next wave of infrastructure, which is something I call the digital object infrastructure. So why don't we stop now? Take a shot. Okay. Well, that's good news. We haven't lost 3/4 of the audience. Okay. What I'd like to do in this next segment is tell you a little bit about this digital object infrastructure notion, which is a way to deal with the organization of networking and communications capabilities around processing and content.
I think somehow one of the switches you didn't get on again on your the audio here.
Didn't touch it, but let's see. Is that better? Yeah. All right. Okay, and I'm told my laser pointer has now been fixed. Good. Okay. So this whole topic really came about from some early ideas that we had in the late 80s about agents, which we call NOBOT programs, and later some work on digital libraries that came about through some work that we were doing with the Copyright Office at the Library of Congress. And many of the issues there seemed to really call for a higher level infrastructure that was more geared to dealing with information than just moving bits around. And so what I'm going to talk about is this architecture which involves the notion of a digital object. I'll tell you what that is. And these objects are things in which rights, interests, or value may reside. And they have unique persistent identifiers so that they can be treated like a retrievable commodity in the network. And once created, these objects can be retained indefinitely if desired. And the user of it doesn't have to necessarily know where they are, because you can always find it from these unique persistent identifiers. So there were 4 goals in this work that I wanted to mention here. One was seeing if we could find a way to make information on the net a first-class citizen. I mean, today, there really isn't. I mean, you almost don't know within the network what you have. It's sort of up to the end user to figure out what it is and how to interpret it. The whole idea of managing access to this information when it's on the net, supporting malleable content, that is, content that can be changed by others, and not necessarily by having formal interactions with the owners of it, but because they put it up on the net in ways that allow you to do certain things and still track rights and interests. And then a final goal that I had, simply because I was so exposed to the legal side of this right up front, not so much because of the fact that we were dealing with the Copyright Office, but because the fact that copyright was so much a part of making information available on the net that intellectual property concerns really dominated. Now, I came at it from a technology point of view, but I was very fortunate that my wife, Patrice, who is a copyright lawyer, also looked at it from a copyright point of view, and I could easily see the magnificence of sort of the legal structures that had been built up over the years by her tutelage. She's sitting over here in the second row on the left, so Patrice, thanks for that input. And so what we've done is sort of work together on trying to align technology and legal systems. If you try and get sort of crown jewels from any company that's in the intellectual property business, like Disney stuff or whatever, you find that the access to that information is more controlled by the legal side of the systems than anything else. And so any technology that doesn't really conform with what the legal systems are prepared to deal with probably can't work. Now, historically, what's happened is that people have tried to be overly protective. My view is that the internet offers an opportunity to actually change the paradigm for which intellectual property is put out there, but nobody who has really valuable intellectual property is going to be willing to let it go out there unless they have some evidence that their basic financial interests, if not their moral rights or whatever, will be adequately protected. So this is going to be an ongoing thing for a while as we develop it, and I just want to give you a glimpse into it. So some of the issues. If there is intellectual property on the net, what can you do with it? I mean, today, most people who pull things off the web probably do what they like, but they have no idea whether it's legal or not. And if you were to take it and put it in a pamphlet and mail it out, you just don't know what you can and cannot do, whose rights you're trampling on, or whatever. If you pull information off the net, how do you know that it's not been altered in some material way? Today, you can't tell. If you were a rights holder, how do you control your information in the network environment? And this was actually an interesting issue that came up in dealing with the Copyright Office. In order for them to grant you registration of a claimed copyright, they basically require that you send them physical artifacts. So if it's a book, you're copyrighting the work that's manifest in this book, you've got to send them the book, and they keep it. I mean, if you go into the basement of the library, as far as the eye can see, there are these artifacts. Some come in through the regular deposit collections of the library, some come in through the Copyright Office, but the fact of the matter is that for copyright purposes, you have to send them physical artifacts. So my notion was, why not send them digital objects? And as long as these objects were in some library that was guaranteed to be accessible on the net, why shouldn't that be as good as giving them a physical artifact? Because they could always reproduce it on demand. Furthermore, they could always tell what that object was if they had some appropriate verification technology, like a cryptographic checksum, so-called fingerprint on the object, which they could store at the library. So if you ever submitted one of these 10, 20, 50, 100 years later, they could verify it and the date. Be just like giving them something physical. And we actually built that system for the library. It's now up and operating, and people can, in fact, send digital objects to them over the net. What it did not do was cause the library to instantly say, we don't want the physical artifacts, however. So even though they now have the ability to not collect them, they're still collecting them. So maybe that will change. They recently made an agreement with UMI, University Microfilms, which collects PhD theses and has rights to, I think they had the distribution rights for them, but they may have other rights as well. They made an agreement with UMI that UMI would keep a qualified repository and always make it available. And if for whatever reason they went out of business, they'd contract with somebody else to do the same. So it will always be out there, and they can always retrieve it. I do not believe they're actually keeping the university theses at the library. But when it comes to MP3 recordings, which they're now starting to take, they actually want them on CD-ROM, too. Okay. So what I decided to do was to focus on libraries for a number of reasons. One, we actually had a large grant from the government, actually from DARPA, to help build library collections at some universities. And as part of the research there, I set out some objectives that were very much like the internet objectives that I originally formulated back in the early 70s. So One was that any material that was stored anywhere in the library system was accessible from anywhere else in the same way that the local material was accessible. So if you had a local library system that you had learned and the material you wanted happened to be on some other one somewhere, you could access it as if it were on your local library system, and you shouldn't know that it was somewhere else. Seamlessly as interacting through 17 nets on the internet or whatever. No fanfare about manifesting the material. So wherever it was, somehow when it comes to your system, you can bring it up. You don't have to worry about how do I actually access the content that's in there. No limitations on time frame if the material and its supporting systems are managed. And I'll say a little bit about what I mean by that. The idea is that if you come back 100 years from now, and let's say you had the identifier of some digital object, or a CD-ROM and a CD-ROM player that could still work, then by accessing that object, you will be able to go out onto the internet and get the object, even though the domain names may have changed 40 times or even disappeared. It might have been on 17 generations of machines elsewhere. It might be in 53 locations, and you don't know any of that. The system will automatically go out and get it. One of the things that we decided to do was to defer trying to define any notion of searching right yet or creation of material, partly because authoring tools are still in a state of flux. We really don't understand what future creativity will look like in this arena. And the searching issues really depend upon how the rest of the infrastructure gets into place. But we did want to encourage third-party value-added services. In fact, the whole capability could be provided just like almost every piece of the internet is now provided by a third-party value-added service provider. So here's a way of thinking about it. If you take a look at this side of the picture over here, this is the internet example where these little green circles, think of them as independent heterogeneous networks. And the internet objective was to make that whole collection into a single network, a seamless whole, where the objective was best effort packet delivery from machine to machine. Now, here is the general problem that I'm posing here, and I see some of my words didn't come out, but this should say heterogeneous information systems, and this should have said heterogeneous networks. But these are now information systems in here, and the question is, can you federate a lot of independent heterogeneous information systems so that it all looks like one? Well, this problem is very abstract and very general, and so the reason I focused on digital libraries is that these can actually be heterogeneous digital libraries. You get some simplification of the problem by at least having a tangible notion of what you're dealing with for starters. So that's what this is all about. It's trying to get this notion of seamless interoperability at a higher level. Now, in order to further de-scope the problem, I guess is what I should have said, you have a whole bunch of problems here. One is that you can ask arbitrarily complex queries of a digital library system. And so rather than trying to deal with arbitrary complexity, what I said was, let's deal with zero complexity queries. I have to tell you what I mean by that in a moment. And obviously, as the query gets more and more complex, I presume monotonically the time to resolve the query goes up. So if the question was, how do I find yesterday's Wall Street Journal? That's a lot simpler question than finding the first book written on rural electrical lighting in America, because you almost have to research to figure out what that book is, or search every book in creation. And that's probably harder than what were Thomas Jefferson's favorite books. I mean, not even clear that you could find a place to answer that question, although maybe that's answerable. So some of them become just very time-consuming to resolve, and some may not resolve at all. So a zero-order query is sort of a query like, who's buried in Grant's tomb? That is, the question ought to almost answer itself, and it has to do with these unique identifiers. And so if I have a unique identifier for a digital object, zero-order query is, how do I find the object whose unique identifier is X? Because if I can't deal with that one, I'm certainly not going to deal with a more complicated question. Now, to further complicate things, this is something that has occurred over our breakfast lunch and dinner tables for years are what these words mean, you know. What does is mean and so forth. What do these words mean? Well, copy is one of those words that, you know, people in the technical fields, an engineer understands what copy means. You see, you know, send something over the internet, you know, and somebody made a copy of it over there. What is it a copy of? And is it a copy? Did you actually send a copy over the network? Well, in copyright, in the legal world, copy is a physical artifact. So you'd never say, I sent you a copy over the internet. That's just not a parsable sentence, right? Unless you could fit a CD-ROM through a fiber. On the other hand, distribute is another one of those words. In copyright law, pertains to the movement of physical goods. So you can distribute printed newspapers, but you can't distribute a physical artifact over the internet. So you could never say, I'm going to distribute my thesis on the internet. It just doesn't parse from a legal perspective. Publish, that's yet another term that's got some of these things. Transmit, reproduce, that's one of those things. If you look at the copyright law, and I defer to my expert here, but I think it says something like it gives you the right to control the reproduction of your work in copies. Right? Not just arbitrary reproduction, which could be anything, but in copies, which means as physical artifacts. Likewise, I'm going to tell you what digital objects are in a moment, but digital objects are really like books. And I presume everybody in this room thinks they know what a book is, right? I'm going to try and now tell you that you may not really understand what a book is, because what you do is, in creating a book, somebody has an intellectual creation. It's called a work, which is incorporeal, and that work then has to get fixed in some form. So the fact that you might think a whole novel and have every single word of that novel in your head doesn't mean that you have a copyright in that work, because you actually have to fix it in some tangible form before you can claim a copyright. Now, the fixation of the book is paper and ink. But that's not the book. The book is, in fact, the logical structuring of the information that took the basic incorporeal idea. Gone with the Wind, as a book, can also be turned into a movie. Well, they didn't actually take each page and turn the pages. It's not like this videotape is here of, you know, watching the pages of the book move. They actually took the basic notion, which was incorporeal, and recreated it in a different form. So you have the work, you have the expression of the work in some kind of logically structured way, and then you have the fixation of it in some form. The book is the logical structuring of the work. The fixation is paper and ink. Got it? Okay. So the digital object is like the book in the sense that it's the logical structuring of the information, but it's not the fixation. So you can print the digital object, you can cause it to come out in some form, in a physical form, but it's the logical structuring that corresponds to that. So anyway, in order to get started on this, you really have to clear away this massive confusion and start, you know, get all the literary words that don't have confusion, like instance and, you know, manifestation and things like that. So can't use the confusing words. So the key attributes are digital objects, which are really structured information. They have persistent, that is, come back in 100 years, they're still okay. Unique, they resolve to one object. And they're resolvable, which is, given an identifier, you can resolve that to find meaningful information about that object to do something with. And I'll say a little bit more about that. We call these unique, persistent, and resolvable identifiers handles. But that's really all they are, as identifiers. Digital objects don't exist in a vacuum, just like files don't exist because you think of them. File doesn't exist because you type a few keys on a keyboard. You actually have to name the file and put it in the file system before it becomes a file. You actually have to give a digital object an identifier and put it in a repository before it becomes a digital object. Okay, so in that sense, think about it as a file. But it can be put in lots of repositories, and you don't have to necessarily link the two together. You can give it a handle and then put it in a repository, put it in a repository and give it a handle, or do it all at once. So it's got to have those properties. These digital objects have stated operations, which lets you understand what you can and cannot do with the object, if the rights holder cares to stipulate any of those. And it's an open architecture system in a network environment, so it's got most of the properties that the internet does. This is what a digital object looks like in in a very abstract form. Keep in mind that when people build repositories today, most people will build them using object-oriented systems. So the actual structuring of the object depends upon how the object-oriented system maps the high-level structures into the low-level bit structures. But if it were bits on the wire representation, it would look something like this. You have in the digital object a number of different elements. One of those elements is the handle of the system. So one of these things is clearly the identifier for it. You probably have a header on the object that will tell you things like the date time of dissemination, the origin of dissemination, the time to live, and so forth. If you ever watched a screen on a TV program, you might see something like, this is the Disney movie that's on ABC, but you also have a local TV station, Channel 7 or something. And so you actually have multiple identifiers. You know, it was disseminated from the local TV station, but in fact, it originated from ABC programming, and in fact, you can derive the sources beyond that further. So you have the same sort of thing here because this is intellectual property, and it's just being presented through the internet as the delivery vehicle rather than over the air or cable or whatever. So the same kind of identifiers can come into play here if you care to trace that. And the types here, this might be a type that turns into, let's say, a JPEG stream, or this might be something that's encrypted. So you can actually tell what these elements are by virtue of the fact that they all have types. So every element has a type, a length, and a value. So you can, the value is what's manifested by the type. Now, if you don't know what type of thing it is, you resolve the type as well. So you can resolve the identifier to get to the element. You can also resolve the type of element to find out what to do. So if, let's say, I put out something and it's of type con, and you've never heard of type con before, you can resolve con to find out. You run this program, which it'll identify for you, against the value in that element to actually manifest the content. So you don't have to worry about standards bodies defining standards anymore, because you can go on to then automatically do the resolution yourself. So that's a very nice feature. In terms of system architecture, this is what came out. I'm now actually reporting the abstraction of our digital library project. We funded Berkeley, Stanford, Cornell, MIT, and Carnegie Mellon to build digital libraries. They all build different ones, 5 different kinds. And every one of them had a repository where they stored their materials. Every one of them had user interfaces. And these were not necessarily web browsers, because they had very different kinds of interfaces that they were getting to. They all had basically some means of authoring, maybe multiple means. We took that off base. I also took off base the whole notion of how you do searching here. And I added these 2 components. The handle system being an indirection mechanism, because in almost all those systems, the interface assumed that what they wanted was in their repository. And the repository is usually one machine, but absent that, it could be anywhere, and you need to know how to find it. So the handle system is basically an indirection system that lets you take an identifier, map it into context information about either the digital object or other network resources. And the registries are just special kinds of repositories that have authenticated information of some kind. Oops. This is what the repository looks like. This is what I call a core repository that has, think of this as like a memory chip in a computer architecture. The only thing you can do with the memory chip is you can put something into it and you can take something out of it. Okay? And what you do is you build up virtual systems on top of that in order to create a file system or a virtual memory system or what have you. So in this case, there are only 2 things you can do to a core repository. Is you can deposit a digital object. Here's a little digital object here. And you can deposit it with a handle and some appropriate service request. It might say, put it here, or it might say, put it to these other places so it can further reposition it in the network. Or you can access a digital object. Now, one of the interesting things that we debated early on was what to call this. A lot of people in the computer science community wanted to call this command retrieve, sort of like you treat the repository like a pantry shelf. My argument was we ought to treat this more like a kitchen. and a restaurant. When you go into a restaurant, you don't say, get me a can of spinach, and they go and put a can of spinach on your plate. What you say is, you know, what can you prepare, or do you have spinach? And if they say yes, you have some service requests that you make of the kitchen, and therefore you've accessed that food via this path. So you're never getting what's in here. And in fact, the right paradigm is what you're doing with an access command is running a program against the digital object to produce an output, which we call a dissemination. So even if you wanted to get the identical set of bits that were put in there, what you do is you'd run the program that produces the identical set of bits. You don't ever go in and get the actual object itself. If this object were the movie Gone with the Wind, and you wanted to get only the first 2 minutes of Gone with the Wind, one model is you could store a digital object that's the first minute of Gone with the Wind, another one that's the first 2 minutes, another one that's the first 3 minutes, or one that's the first 0 to 1 minute, and one that's the first 1 to 2 minutes, and so forth. But in fact, it's a lot easier just to store the whole thing and run a program against it to extract the piece that you want and produce that. And so there's some issues about exactly what's allowed in terms of the service requests, but fundamentally the access mechanism is to run a program against a digital object to produce a dissemination. The disseminations look like digital objects, but they may never have been stored, so they aren't literally digital objects in the formal sense as I defined them a moment ago. That's what a repository is. The repository has not only the object, it's got some other things associated with it I didn't show here. It's got the properties record that essentially lets you keep track of the metadata for the object. It's got a transaction record that lets the owner of that object know what's happened to it. And it's also got, in principle, although we've never built it yet, all of the tools to manifest the content of this. If you think about what you would do today if somebody gave you a VisiCalc spreadsheet, do you think is there anybody in this room that could manifest a VisiCalc spreadsheet? Does anybody remember what VisiCalc is? Anybody here that could manifest it? Probably not. Because one, you probably don't have the software. And even if you have the software, it probably only ran on a really old IBM PC or something that you probably don't have either, unless somehow it was upward compatible all the way. So you not only need to have the tools to manifest it, but you need the environment in which those tools run. And think about coming back 100 years from now. I mean, VisiCalc is only, what, dates back to the early 1980s. That's only 15 years. In 100 years, lots can change. And there can be lots of repositories, and in fact, repositories can interact with each other and so forth. But it's called a core repository because you can actually nest repositories. So the core is at the middle. Here's a larger repository that knows about the structure of digital objects. So at the core level, all you can do is run simple kinds of commands against it. You cannot know the detailed structuring of the information within the object. But at this level, you might know that this is a book, for example, and it's got tables and it's got pages. So you could go and say, give me page 3, page 7. At the digital object level, you might not know about pages any more than if you took a linear stream of the book, you'd understand where the page breaks were, things like that. Content level, well, you might want to go in, if this was videotape, and say, show me the places where Jimmy Carter is speaking. And so it now needs to be able to understand the semantics of what's going on to be able to retrieve that. And then you've got other levels. Aggregation and deaggregation is actually very interesting. It's where you either try and produce a dissemination by aggregating multiple digital objects to produce your output. Like one object could be a choreography, another one could be a characterization of a cartoon character like a teddy bear, another one could be a stick animation diagram, and you want to produce a dancing teddy bears, and somehow by putting all of these different digital objects designed by different people together, you could produce it. Deaggregation is the other side of the coin. It's where you put in something that looks like it's a monolithic thing, which breaks it up into lots of elemental pieces and files them appropriately. So let me say a little bit about the handle system. This is actually a system that's on the internet now and has been since 1974. So for those of you who were pleasantly surprised to discover the internet in 1993, I don't know if it would have helped for you to know that it was around since the early the middle 1970s, but the handle system may very well be a very key piece of infrastructure within the next several years. The publishers are using it widely for identification of their books. They call them digital object identifiers or DOIs, but it's really handles. They just have labeled, just like United Airlines puts its name on the side of the plane instead of Boeing. It's still a Boeing aircraft, and the DOIs are still handles. But it was really the very first general purpose indirection system on the internet, and it provides user-defined state information back to the user, and it's really been optimized for speed and reliability in doing resolution. What we tend to do is identify repositories that contain digital objects. So given a handle, the information that comes back will give you the IP addresses of, let's say, the 5 repositories that hold that object. So if these objects were, let's say, web pages, you could put the web pages in 100 countries around the world. Somebody could go in and find which one was nearest to them, easiest to access, fastest, or whatever. Furthermore, if everything changes, the user's view of the world doesn't, because users have a single unique identifier for that object, and even if the object were moved every day, it would always resolve to the right thing in the right place if it were managed. And that's what the publishers are doing. The music folks are about to do that as well. But more generally, since the user can define what the state information is, it can provide indirect references to many other things as well. So we're looking at it for the purposes of locating individuals, their fax numbers, their pager numbers, their beepers, their cell phones, their addresses, or we're also looking for using it in a variety of applications involving certification, whether of the conventional kind or the spooky kind. That is the simplified public key interface kind. Okay. The reason that you need something like this is the current systems are all really limited. If an object moves to another machine, the basic domain name will be different. So if you're using email, the email won't go to the right place because it's addressed to a particular machine. URLs won't work because they identify a particular machine. If today you have objects on multiple machines, there's no way to tell that to them except through something like the handle system. And neither mailboxes or URLs are managed, and the handle system is just the easiest way to do that. It's on the internet, and anybody now can use it for free, so there's no problem with that. It's all supported by DARPA. In terms of resolution, this is also a confusing area because people don't realize that there really are different aspects to it. One, a registry of assigned IDs is really what you need to assure that there are no duplicates. In principle, you can do that by an algorithm or a formula, but if you're just letting people pick numbers themselves, then you probably need a registry. A means for resolving the IDs, and by resolving it, the question is, what do you get back in this user-defined state information? So that's an open issue. And a means for managing IDs, namely generating them, deleting them, changing them, and so forth. These are 3 independent pieces that people often bundle together in various combinations. Now, just briefly in terms of format, handles really they're really pretty simple. They've got a prefix, a slash, and then a suffix. And the prefix is just a unique identifier for the organization that is providing the suffix. So in the case of the publishers, they could use ISBN numbers, they could use anything they darn well please. We tend to use date timestamps. So a program could identify anything by just reading the clock, and using the clock information in it. And because there is a central place where these things are all put in, no 2 programs could ever put the same thing into the registry at the same time. Just wouldn't be allowed to happen. The handles are opaque strings, so you can actually have semantics in here, but the handle system ignores it. And this was a big point of contention with the universities who actually wanted the visibility. So if this were an MIT thesis, they would swear on a stack of Bibles they'll never sell MIT theses to Stanford, and vice versa. But if this were McGraw-Hill might very well wish to sell a publication that it has the rights to Simon & Schuster or Prentice Hall or somebody else, in which case they didn't want any trace of semantics in the identifiers. They didn't want its lineage to be exposed. So the publishers insisted on numerics, the universities insisted on semantics, but in the final analysis, the system doesn't care. So you can have combinations in any of those directions. I'll show you some examples. Let me say about how the resolution is done, because it's actually done with a flat system. It can have multiple levels, but doesn't need it. So you can imagine all the resolution done with a flat system that happens to be scalable, and at the same time it's logically centralized, but it's not physically centralized. So you can have n servers, and what happens is when you insert a handle, the handle gets hashed to figure out which of these servers to put it into, and that becomes the one that's responsible for management of that handle. And then it can be backed up in other servers for reliability. And when you go ahead to resolve a handle, you run the same hash on the handle to figure out where to go, and either that one will do the resolution, or if for any reason that one is down, you will have an offset to go to another handle server that software automatically computes. So this is actually very, very reliable, and gives you a uniform distribution of the handles in the system. So this is how you can group things. This might be, let's say, a group of handle servers in the US, and let's say that's the primary server for a given handle, and it can have secondary servers for that as well. So if you were going to resolve a handle and you were in the US, you'd probably come in here first, then you go here, and then you can decide which of the other groups of servers to go. This might be a European set of servers, that might be an Asia Pacific set, and this might be other, and so you could say, go into this one first, and if you can't resolve it here, then go here, then go here, and then go here. And so, you know, wherever you are around the world, you have an efficient way of doing it, and if that's all broken for whatever reason, you can go somewhere else around the world. And because you can pick the numbers here, you can really engineer the number of nines that you wish. I've got a light right in my face, but I think there's a hand up there.
Question, would you consider this a level of domain name service that's a level above domain name service?
Yeah, I would consider this close to a third level. I mean, because of the complete flexibility you have in providing state information about the objects. Because you could identify an object by icons on the screen, and all the handles can be invisible below and therefore just completely clickable. It could be on a CD-ROM and clickable, and you'd never have to know about the notion of a domain name. The reason people like domain names is that, you know, you can advertise it on the radio. You can say, you know, click phones for sale, and people can sort of remember that and type it in. But I think there are probably more ways that this can be used where people can, as part of their advertising, download something that you can then click on. So you're dealing with more of an iconic thing than anything else. And it can even be true in email, as you can have images, and those images can then resolve to who the end parties are, and you can even get certifications on what those entities are if you want. The administration is also pretty interesting here, because unlike today's system where you have to go to a registrar to put something in, all you need to do is once be given the authority to be able to create handle records, and you can do them yourself over the internet. So for example, here's one for a given university. Let's say they've got approval to be a top node, and their prefix was UNIV. Let's say nobody else in the world happened to have that. They could then create, by a dotted convention, they could create one level down, something like univ.csl. So if they wanted their computer science lab to be able to create it, they could create a whole new administrative record for somebody here. Now they would use the handle univ.csl to do it, and likewise, that layer can generate third layers and fourth layers. In fact, it can go arbitrarily far down. So a given organization can delegate to the different parts the ability to do this themselves, and those individuals can then put the entries into the handle system themselves. Doesn't require any central administration. So it's very cost effective in dealing with it. Here's the way we prefer it, as if it were done numerically, so that you don't run into the semantic conflicts. So if this were 1217, this might be 1217.42 or .1, and this might be 1217.42.3. And so it's a dotted convention on the left side, and it's anything you want on the right side. And also notice I show that you can do all the mixes. Here's semantics and semantics. Here's numerics and numerics. Here's semantics and numerics. And here's numerics and semantics. So it doesn't really matter. It's just looked at in the handle system like an opaque bit string. So let's just say that of the many issues that remain here, these are some of the ones that I'm particularly interested in. The whole issue of how we deal with security and cyber crime and terrorism, the whole issue of intellectual property protection, not only in terms of knowing what you can do, but also the enforcement side, the issue of privacy and dealing with disclosure of data and tapping. I'm very interested in this taxation issue and how that plays out. I'm hoping that they find a way to not tax the internet, but it looks like it's coming. The whole area of ethics on the internet and of course national security is one I'm very interested in as well. So just in closing, we'll take a few questions. And when I think information technology really is going to be critical in the 21st century, that the infrastructure is really the engine of economic growth for this whole field. I think the internet will be the information marketplace for the indefinite future, and that we're going to be dealing with a constantly evolving set of technologies and new applications. The only stability in this whole thing may very well be the meta-level architectures that cause it to stay together. And that my real hope is that new modes of creativity and expression will be invented, along with all the new kinds of e-commerce and sophisticated applications that we can develop. So given the amount of time, that's as much as I could fit into it, and I appreciate your patience, and let's open it up to questions. Thanks very much.
We'll entertain questions. I'd ask Dr. Kahn if you would repeat the question so it would be on the tape.
After their
If all the information will be kept indefinitely, is it possible that the amount of information will grow up so fast that the speed of the computing power will not be able to catch up with it and not be able to access that information?
Well, first of all, what I was describing was a mechanism whereby it was possible to keep any piece of information indefinitely, persistently. I'm not arguing that you should keep every piece of information indefinitely. In fact, I would certainly argue that one of the hardest things for most people to figure out is how to get rid of information intelligently. I think that's a very hard thing to do. It's just a lot easier to archive it. On the other hand, are you a mathematician at all? Do you know about, Poisson processes where you have things that happen in shorter and shorter time frames, but larger and larger energies, and the product of those two is constant? I mean, it seems to me that the real question here is, will the cost of memory and storage go down faster than the amount of information that we grow, so that the net effective cost of keeping everything stays constant or even goes down? If that's the case, it may turn out to be economic to literally keep everything if you want. If it turns out that information that you want to keep is going to grow faster than the cost of buying the memory or replacing your memory or whatever your economic strategy is, then it won't be economic to do it, and we'll have to get into that issue. But so far, the cost of memory has been coming down pretty dramatically, and people have not really gotten into acquiring information that fast. That could all change. I mean, with all of the wearable computing that's now coming about, it is conceivable within the not too distant future that you may be able to capture your whole life, not you, because you didn't do it for the first 20 or 30 years of your life, but in principle, you could wire up a baby, with their baby clothes, and they could have a record of everything that ever happened in their life, from no years old on, and put that in an archive, and one of those people will surely be president of the United States sometime, and they could go into their archive and show the whole history. And for most people, you'd probably throw it away. I'm not proposing that either, but it's possible. I mean, you can imagine it. Yes, question over here. Is this a prepared question?
The lady defers to me.
Absolutely.
I took the trouble to write this down. The National High Performance Computing Act, the HPCA, is believed to have laid the foundation for the information superhighway, and the government is expected to take an active role in the future of information distribution. Now, can this be done without politicizing the process or otherwise hampering rapid growth?
Well, look, anytime something is so important to society politics is going to come into play at some level. You just can't avoid that. And I think it has nothing to do with an act of now or 10 years ago or 10 years in the future. I think we were very fortunate in the way the internet played out. I mean, I'd like to take some of the credit for having come up with a plan that allowed for this devolution over time. Just like in describing the digital object stuff, I could see how that could all be done by other parties over time. But I think that the fact that the government gets involved in some part of it typically will mean that they'll have some custodialship for a while, or at least some paternity for a while. And I think as far as the internet is concerned, it's mainly gone to zero. I think they're going to be concerned with the kinds of things that governments are typically concerned about for things that go on in society, because the internet is now becoming a reflection of just about every facet of society.
Well, when you were working with the ARPANET, everybody's heart was in the right place.
I don't.
We're all trying to accomplish a mission which the government needed. Look, today they can't even fund the next month of operating the government, so that's what worries me. A follow-on question is, since Vice President Gore promoted the HPCA in 1991 and was instrumental in getting the White House on the net in 1993, would you find it appropriate to honor him with the title Godfather of the Internet?
I think he deserves recognition for the important contribution that he's made, which was to help push this whole field forward. He's been a strong articulator of fiber optic networking, probably going back into the 70s. I think it's probably a legacy from his own father, who was sort of the force behind the federal interstate highway system. And he's done probably as much as any politician, if not more, to push this whole notion from the federal level. But I would like to refrain from, anointing anybody with notions of paternity, meta-level paternity, or whatever the inverse of meta is, simply because it serves no useful purpose, in my view. I think what people have done ought to be able to be articulated, and people ought to be able to stand on their own accomplishments.
Thank you.
Yeah.
Do you see security being controlled by the digital object handle, by access to the repository, or access to the program that creates the instance for you?
Well, we can have an argument about, or at least a discussion about what we mean by security, but if you're talking about making sure that the party who is accessing an object has permission to access it, is that the fair?
That's a good definition.
Then I would say that's handled by the negotiation in the repository between the user and the repository when he makes a request to access that object. There's something that gets invoked at that point. We get into lots of technical approaches as to exactly how you might do that, whether it's a user typing in a keyboard, another program sending in something, is it coming from another repository? Is it part of a trusted enclave that already has prior approvals and therefore is okay? Is it coming from outside? So depending on what the situation is, I see it still being mediated by some program at the level of access to the object. Yes. Question here?
First, a comment, and then a question. A comment that was generated by my colleague here. In light of the views on Gore's contribution in the early 90s, considering the ridicule he's been put through publicly, as far as laymen, they don't know one from another, including me in this regard. Somebody should write an op-ed article giving him due credit. Maybe you, maybe you.
Or you.
No, I don't know about it. In fact, I'd like to ask a question that may sound naive, but you mentioned speed, reliability, and I wonder about duration. You mentioned creativity and new expressions of formats to come and so forth, and then you also refer to 100 years from now. Well, I won't be here in 100 years, but I wonder, a book as we know it, a print is a book, whether it be the Guggenheim Bible or a series of clay tablets. But 100 years from now, all the technologies that we're using now, regarding even repositories and archives and so forth, will be inoperable, indecipherable to the people 100 years from now. Someplace there should be archives or museums that I should think that would preserve the technologies today or even 10 years ago, so somebody 100 years would have something to work with. Am I way off base? I don't know.
No, you're actually right on base. But you're making an assumption there that may not be right, and that is, I think the implicit assumption is that you need to physically have the technology in its then instantiation 100 years from now, and that may not be the case. If you had a piece of software that was needed to manifest some information, one possibility is, and this is an area of very active research now, I might point out, one possibility is to literally preserve that piece of software. Since it's just bits, you can guarantee that you can preserve that software. What you also need to do is to preserve the environment in which it runs. It might be the operating system that it was designed for, if in fact that's the case. It might be a virtual machine environment, like a program written in Java. It might be for the Java virtual machine. And then you need to, if it's something that's tailored to a particular piece of hardware, you need something that's probably going to emulate that hardware. Now, if it's a Java virtual machine, you can continue to create. That's one of the advantages of something like that. You can create the virtual machine environment by virtue of its specification and continue to maintain that over time. The other thing that you can do, and there are strong proponents of this and strong objections to it, is you can literally take that information and convert it so that it runs on a more modern system and keep doing that. The question that comes up, and the reason that people object to that, is there's no way to guarantee that every time that you do that, you will literally maintain the exact shape and form of the original. And you can probably do it in a way that maintains its content. If by content you have a narrower definition, like every character in the book was adequately reflected, it probably doesn't matter. But if you want to know what the Declaration of Independence actually looked like with infinite precision or very fine-grained precision, then just simply putting it off won't work unless somebody is almost curating that process to make sure that every conversion step maintains everything that was there before. And I don't think in general that's always going to be possible. So I think you're going to see a hybrid of these. For some things, people won't care whether it's in the original form, or as long as it's close enough, it will be good enough. In other cases, they'll want to literally preserve the original as it was done, and they will therefore need to preserve also the environments and the programs that will manifest it. And I think that's an interesting tack for the libraries as well, because storing the artifacts is only one part of the story. Storing the means of manifesting those artifacts is the other side of the story. Yep, back there.
Does Corva have a place in your digital data objects, even so,
Well, actually, we've done all the implementations using Corva as the basic vehicle, using some of the tools that have been developed in Corva. But the design of this thing is independent of any particular language. In fact, the notion is not really rooted in object-oriented programming at all. You know, another interesting thing is if you look at the internet architecture, the notion of a gateway was a virtual concept. If you read the original paper that we wrote, you know, the notion of a gateway defined a mapping between two systems. What had to happen there, it didn't define any piece of hardware, it didn't define any piece of software. It just sort of functionally described what had to happen. And that's one of the reasons why it's sort of technology independent. The repository is exactly the same way. Nothing in this definition says what the hardware or software of the repository should be. It just says it's got to support these interface commands coming in for access and deposit at the core. And if you're building higher levels of these nested repositories, they can have more functionality, which we haven't tried to specify here purposely. but they must support a deposit and access command so that you can always make those commands of any repository, even if it provides a higher level of functionality. So it's a very interesting question as to how you deal with alternative programming styles in the future, particularly those that haven't yet been invented or developed. But my hope is that by use of a meta-level typing scheme, even on the wire, you will be able to specify that in a resolvable way. So you can say, when this is coming down, this is a bits on the wire specification, and the other folks will know how to respond to that, or this is a Corba implementation, or this is done in the following, this is done in Python, or this is done in ActiveX, and people will therefore be able to interpret it at the other end. See if anybody else that hasn't yet asked a question. Right there.
What impact on the internet would you have if you did away with the copyright laws?
I don't know how to do that. How do I do that?
Well, I mean, right now, from what I can see, you're structuring the internet because you have a copyright law. That
No,
seems to be a
no.
problem.
The internet,
Or am I reading it wrong?
the internet is there, and there are various laws that apply to intellectual property. They are both fixed
But
point.
if you did away with those laws, what impact would it have on the technical aspect of the internet?
Well, I mean, it wouldn't change it any more than, you know, if we did away with the sun, it wouldn't change the design of the internet either, but it might have some other effects. I mean, I don't know how to deal with the premise of your question, because we deal in a legal system. And if you're saying, could the functioning of the net be made different if certain legal constraints were removed, the answer is it would probably enable things to happen because people wouldn't have to worry about certain liabilities that they now do. But from a technical perspective, the basics of the internet probably wouldn't change. If we built a system that enabled the laws to be effectively used so that people could still get the protection of the laws and make their information available, and then those laws went away, you could imagine the technology being simplified so it wouldn't have to deal with those things. But I just don't think the premise of getting rid of fundamental laws is likely to be a starter of any sort, because we just have to deal with them. They are there. Yeah.
As you can see, this particular chapter deals with microwave issues and, in fact, quality of service issues. We've done that with cellular phones, and sometimes they're not too great, but in any event, what
I like mine.
see as the networking? What happens when errors get into this system? I mean, what level of errors can we allow? We're not going to be 10 to the minus 12-bit error.
Well, let me try and separate out a couple of issues we're talking about. You can talk about errors in communicating information from one place to another.
Yeah.
And fundamentally, you can control that. I mean, we have within our power the ability to control the reliability of that if we don't care how long it takes for things to get through. Right? So if we're willing to trade off delay for some delay and or protocol for handling things, you can get arbitrarily high reliability. So that's known. That's a fact. At the level of what kind of errors you can tolerate with information once you have the information correctly in hand, seems to me that's an unbounded problem. It's like, what kind of imperfection can you live with in your life? Okay? Could you answer that for me? I mean, I don't think that's a manageable question. I mean, are we talking about the fitting of crowns on your teeth? Are we talking about the quality of your relationship with your friends and family? Are we talking about, you know, the quality of the food that you eat? Are we talking about your resistance to disease? Are we talking? I mean, it is so broad that I mean, the bottom line, I think, has got to be, can we use this technology and this whole environment effectively to support societal needs? Speaking broadly. And if it turns out that it is an effective, efficient, productive, cost-effective way of doing that, then I think we will come to grips with the imperfections as they're identified, that people are not willing to put up with. I mean, banks are not going to put their records in a form where they can be compromised. So they may take some protection measures that you would never do and never be willing to do, because for you it might not matter as much, but it might for the banks. Or if it were national security, they might take yet a different set of strategies. I think we're going to have to deal with issues of cybercrime. And I think that's a much more serious kind of thing than issues of just arbitrary error, because if an arbitrary error occurs somewhere, almost surely we'll have the means to track it and find out what happened. Or if not, the legal processes have enough sophistication in them that you can take enough depositions from enough people and go and inquire and find out what really happened. As long as people are willing to work with each other toward those ends. And if it's just plain error, I mean, you go to your bank and they'll sort things out, and if it's plain error, you can go to your local watchdog. But if you're dealing with issues of cyber terrorism or cyber crime, now you're dealing with a whole different set of issues here, and I think one of the dominant research themes, at least for the Defense Department and others, is going to be how to deal with these kind of issues. These are not errors. These are either willfully hostile attacks or subterfuge of the sort that you may not even know is error. That's really the big ticket item for me. Yeah.
You talked about, I think, commercial applications for a synergizing, say, healthcare provider, doctor, insurance company. A couple weeks ago, there was a company started with Jim Clark.
Healthy On.
Healthy On, yeah. Is that what you're referring to there?
No, I wasn't. I mean, I think Healthy On is an example of a company that's trying to engineer a solution. And I think they'll probably be successful. Jim's a good friend of mine, and I think he's succeeded everything he's done and probably succeed there as well. What I'm thinking of is, how does the 11-year-old kid who doesn't know any of the parties and doesn't have all of those contacts manage to do something as powerful as a Healthy On may be able to do with all the wizardry of that by just simply knowing about protocols and standards and interfacing? That's the real power of infrastructure. Yep.
I've got two questions, if I may be allowed that privilege. One was engendered with the comments my colleague Marge made that, well, she wasn't going to be here for 100 years. I'm willing to take a bet on that if I can hold the money. But you'll have things in storage for 100 years. And we talked about the fact that some of these things, the technology would be superseded, and so the environment should be protected as well. But how do you assure yourself that a Y2K problem isn't going to arise? You may still have the information, you may still have the environment, but I didn't see anything that said test this for longevity or some such to prevent a similar circumstance. Is that built into this structure that you were describing?
No, I don't know how to prove this, but I think there's a kind of a Gödel's theorem that you can never predict all the things that can go wrong with something a priori. And that even if you thought you could write the list of every possible thing you can think of that will go wrong, there'll be some other things you didn't, and there'll be some way of proving that, you know, even if you made a countable enumeration of all those things, that there are things that you couldn't put on the list that would still possibly go wrong. So, I mean, should we be worrying about the Y10K problem today? How about the Y100K, Y1000? I mean, you can go on as far as you want, but sooner or later there's going to be some set of issues that will come up which may cause problems, and you can identify them and go after them. The thing that's working in our favor is that computers are getting faster and faster, and the number of problems like this is not growing at the same speed. So I think the real tool that we have to use in combating these kind of problems, once we identify them, is the very technology that's causing the problem itself. And if we can just avoid too much physical hardware that has to be modified over time and put it all in the realm of softer solutions, then my guess is we'll be able to combat each of these once they're developed. Doesn't mean that we won't have some equivalent of a tsunami or you know, a hurricane or an earthquake that will hit cyberspace. Maybe it will, and maybe we'll have to deal with that, but that's where insurance comes in. And my guess is insurance and cyber worlds are going to play an increasingly important role for us in the future.
The other question I had brought to mind when you, in one of the review graphs, you indicated the internet might be used with the utility. And I might think of other essential services, whatever they are. By essential, I mean our life wouldn't go on very well if they were disrupted. Now, if the internet is used in that for such essential functions, then two things come to mind. One you just mentioned, how much damage might an earthquake do? And the other might be more pointed. How can we protect against damage caused by terrorism? Can we?
I think the answer is clearly yes. We can mount defenses against cyber terrorism. Ultimately, the question is, who's going to be more effective? I mean, the attackers or the defenders, the protectors? And this is the classic epsilon delta argument that goes on in national defense at all times. You postulate threats, you postulate ways of reacting to those. You hope the worst of your fears never come to pass, but you're always prepared for it. You know the famous story they tell about the guy who's on the perimeter of this big country, and he's out there, and his job is to keep the invaders out. And some guy walks up to him and says, "I don't understand what you're doing here. There hasn't been an invader in our country in 1,000 years." He says, "See, it works." So.
I think as it's getting late, we've had 2.5 hours with Dr. Kahn here. I'd like to ask for a round of applause, and then maybe he'll stay for a few seconds.
Thank you.
Put you through the
That's all right.
drill.
And I'm just gonna,
Wow.
I think I'm locked in there. Let's see if I can.